Okay, so let's take a closer look at the slicing problem. So to remind you once again from the previous video, you have a pet class, an instance of this pet class called vPet, a dog class which inherits from the pet class, and an instance of the dog class called vDog. We assign the two data members of the dog class. Remember, dog inherits from pet, so it gets the name data member and the breed data member. We set both of them. Now here is where the slicing happens. We say vpet is equal to vdog. At that point, if we try to say vpet.breed, there is no vpet.breed because it was sliced off at this assignment. Okay, so only the pet part of dog remained when we made this assignment. The dog, the exclusively dog part of vdog, was sliced off. We lost it. And so if you call vpet.print, we would get only whatever this print method for the pet class will print, which is, if you scroll down, look at here, it only prints name. And you can run this and that's what happens. You see the slicing problem, you print out this vpet.print and it prints only the name and no breed. Okay, so there was no breed. Now the way to get around this, the fix is to use pointers. So here is the slicing problem sort of fixed. We create not pet objects but pointers to pet, and then we assign we allocate memory for these objects dynamically. Create a ppet is a pointer to a pet object. When we use new to create a pet object, we say pdog is equal to is a pointer to a dog object, and we have created a dog object. We set the name using, remember, our arrow notation for pointers. Name and breed are set, and then we do ppet is equal to pdog instead of doing vpet is equal to vdog. Here it turns out there is no slicing. If you call the print function, here it is, the slicing problem defeated. It prints out both the name and the breed, whereas previously without using pointers we only got the name. The dog part was gone. Here the dog part is intact. Whether we print ppet or pdog using the print function, member function, we get both. There is no slicing. Okay, so that's the big difference. You want to definitely, if you're not sure about this example, take a look and see the difference. The key difference is after making this assignment in the first case we set vpet is equal to vdog. Vpet has sort of a sliced off version of vdog. If you use pointers and dynamic memory allocation, when you make a similar sort of assignment, it's not exactly the same, you just assign pointers, there is no slicing off. That's because these pointers actually have some additional information having to do with the virtual tables and all of that, and we get the right virtual table. That is, we get the dog virtual table in this pointer, which is of type pointer to pet. Then we can use polymorphism just like we did in Java. So in Java, the difference is the Java, it works like this with the slicing problem fixed or defeated. There is no slicing problem like this in Java. You can get similar ones, but nothing like this. So even though the syntax of Java is closer to this, it works like this in C++. Since the bottom line is C++, you have to be careful. If you assume it works like in Java, no. It may not necessarily work as we saw it in Java. Okay, so here's the slicing problem example. Use pointers. You still cannot access a breed data member of ppet. Because ppet is a pointer to a pet, there is no breed data member. However, they both have a print method, and that's what we really want to use. And if we don't use pointers, you call the print method, you can see that it will be sliced off if we don't use pointers. Okay, so this print method should, even though this is of type pointer to pet, it will call the print member function in the dog class because it's virtual. All right, so C++ waits to see what the object pointer ppet is actually pointing to before binding. So that's another way to think about late binding. It waits to see what the actual pointer is pointing to. And destructors work in a similar way. So remember that destructors need to deallocate dynamically allocated data. So if you have something like this, let's say you have a base class and a derived class, and you set pointer to base pbase is equal to new derived, which you can do because of polymorphism. And then you delete pbase, this would call the base class destructor. Even though it's actually, this pbase is pointing to a derived class, it would call the base class of the destructor unless you make the destructor virtual. And actually this is a rule of thumb that's always good. If you see some strange problems with your program crashing when you're destructing objects, chances are you should check if your destructor is virtual. That is, if you have inheritance and all that. And it's good policy for all destructors to be virtual. That is, by default, just make all destructors virtual. There's almost no good reason, apart from that slight overhead in time that you need if you have virtual methods. It's good policy to make all destructors be virtual. Okay, so a quick note on casting. So remember, let's say we have these pet objects, a pet object vpet and a dog object called vdog. You can try to do a static cast to dog of vpet, but you'll get an error message. So you cannot cast something that does not have any dog information to be a dog. Right? That's just plain illegal. You cannot cast a pet to be a dog, but you can cast a dog to be a pet because every dog member is a pet. You can also do a static cast to pet of type dog. So this is called upcasting, and upcasting is okay from descendant type to ancestor type. The problem that you'll run into is probably downcasting. Downcasting has lots of problems. It can be pretty dangerous. That is, you're saying something like this. You have let's just take the opposite. So in this case, you're upcasting. You're saying pet is up, dog is down in the inheritance diagram, and so you're putting a dog to be a pet. That is upcasting, and that is okay. If you try to do the opposite, vdog is equal to vpet, like you do over here, this is downcasting. Dog is down in the inheritance diagram, and pet is above. And so you're trying to do a downcasting. This is actually illegal. There are times when you want to do this kind of thing, but it can be dangerous. Casting from an ancestor type to a descendant type, it can be dangerous. This assumes that information is added. So you can do this with a dynamic cast, and it might work, and it's legal, but it can also be dangerous in some situations. So let's say you have a pointer to pet, and then you say pet is equal to new dog. So although it's of type pointer to pet, it's actually pointing to a dog object. Now it actually does make sense in this one particular case to cast this pointer as a pointer to dog, okay, using dynamic cast. That would be okay. and it's legal. But in this case, it is not. If all you have is these three statements, it's not dangerous. But you can see where it can potentially be dangerous. Downcasting can give you problems if the thing that you're pointing to is actually pointing to just a pet object. So downcasting is rarely done due to the pitfalls because you have to track all the information to be added. You have all member functions must be virtual. Okay, so virtual functions, do we really need to know how virtual tables work, virtual function tables work? You probably don't need to know all the details to use polymorphism. You did it in Java. I'm assuming that you all had Java. You used polymorphism in Java. You've used it. So, but it's good to know that there is this thing called a virtual function table, and the compiler creates it. It has pointers for each virtual member function, and it points to the location of the correct code for that function. Objects of such classes also have a pointer to the virtual function table. Okay, so that's about all I want to say. There's more details on virtual function tables in the book and out online. If you're really interested, definitely ask and we can go over this.